So today we're going to be talking about Avogadro's number, which we talked about Avogadro's number a lot before when we were talking about constants and all these other things, right? But the thing to really know, the thing to really to take away from Avogadro's number is that Avogadro's number relates to the mole, right? So 1 mole is equal to 6.02 times 10 to the 23rd items. That's Avogadro's number. Avogadro's number is 6.02 times 10 to the 23. So what do I mean by items? Well, it could be any item, completely anything. It could be, for example, it's the same as saying, for example, 1 case of Coke cans, right, has 24 cans in it. So 1 mole of something has 6.02 times 10 to the 23rd items in it, right, which is Avogadro's number. Or you can say a ream of paper, 1 ream of paper has 500 sheets of paper in it. Or a dozen eggs has 12 eggs, right? So Avogadro's number, just one more time, just to reiterate, is 6.02 times 10 to the 23rd items of something, right? And we call that in chemistry a mole of something, right? Of course, just a little bit of history. Avogadro's number was named after, or was determined by Amedeo Avogadro. He was an Italian physicist that lived from 1776 to 1856, and we'll be using the mole a lot in this class. So just make sure you pay attention to that, right? Or you remember that. So we're going to talk a lot about a mole of an element, right? So that means 6.02 times 10 to the third atoms of that element, or a mole of carbon, or a mole of sodium. So we're going to be using moles a lot. This is one of those numbers that you're going to have to remember, right? So let's keep going. So really, we use the mole to help us convert the number of moles of a molecule to the actual number of molecules there are, right? So in this particular example, we're talking about some moles of dry ice, right, or frozen carbon dioxide. So the question is, how many CO2 molecules are in 0.5 moles of CO2 or carbon dioxide, right? So remember from the previous slide, we have 1 mole of CO2 is equal to what? 6.02 times 10 to the 23rd molecules. Molecules of CO2. I think I have one too many S's there. So that gives you a ratio that you can use, or a conversion factor, right? That we remember conversion factors that you can use, right? So it can be either, in dimensional analysis, it can either be 1 mole of CO2 is equal to 6.02 times 10 to the 23rd molecules CO2, or you can use the ratio or conversion factor of 6.02 times 10 to 23rd molecules CO2 equals 1 mole of CO2, right? So that's really helpful. That's really helpful because now you can say, like we were doing before with dimensional analysis, start off with what they give you, right? Which is 0.50 moles of CO2, right? Begin your dimensional analysis. We want to know how many molecules there are, so you want to end with molecules, which means that the mole should be at the bottom because you want to cancel out moles. So that's 1 mole of CO2, right? And you'll be using this one right here, this ratio or conversion factor, right? 6.02 times 10 to the 23rd, right? Molecules of CO2. I'm running out of space, so I'm not going to write out molecules there, right? And then when you calculate that using the calculator, this is how you would do it. Let me switch over to, I'm sorry, I'm going to block this with a calculator really quick, and then we'll go back. There we go. I decided to switch over to a different calculator. It's the same, it's still a TI-30 series calculator, but it's blue now. I thought that the higher contrast would make it easier for you to see things. So let's go ahead and calculate this out. Remember, when you do a dimensional analysis, you multiply everything at the top first, right? So 0.50 times Avogadro's number, right? So this is how you would type in Avogadro's number into the calculator. It would be 6.02, which you probably already knew that part, right? Let me see if I can get it out of the glare. There we go. 6.02, and then it's 10 to the 23rd. So this is where you type in second, right? And then, I'm sorry, I can't see anything here. Here we go. E, right, to the 23rd. And type in 23. So that's how you type in Avogadro's number in the calculator. You press enter because you want to do that first. That gives us 1.03, sorry, 3.01 times 10 to the 23rd, right? And then this is easy because the bottom is just 1 mole, so you just divide that by 1 mole. And your answer is then, I'm going to move the calculator out of the way now, since we did the calculation already. The answer is then 3.01 times 10 to the 23rd molecules of CO2, right? Right? And notice, remember, we're still doing significant figures here. There's 3 significant figures there, right? That means we need to have 3 significant figures here. That's 3 already. So we're good. Okay. So now that we've done that pretty simple calculation, let's kind of break down a molecule into its constituent atoms and figure out different things about different quantities of atoms now, right? So next. Sorry, I'm a little bit parched here. So we were talking about the formulas for different compounds last time, and you saw that the subscripts help you write the formulas for certain compounds. Well, the subscripts do more than that. They actually give you the molar ratio of each constituent atom, right? So just so you know, they do 2 things, right? They show you the relationship of the atoms in the formula, right? And they show you the number of moles of each element per 1 mole of that compound. So for example, if we look at this molecule of aspirin right here, right? Look at this molecule of aspirin. Its formula is C9H8O4, and what that means is then that there are 9 atoms of one molecule has 9 atoms of carbon, 8 atoms of hydrogen, and 4 atoms of oxygen. Well, that also means then that 1 mole has 9 moles. 1 mole of aspirin has 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen, right? So the subscripts in the chemical formula are very helpful in that way, right? It shows you the relationship between the atoms and the formula itself. So then you ask yourself, or with this particular example here, we can ask ourselves how many atoms of oxygen are in 0.10 moles of aspirin, right? Well, it's super simple. Right? We start out the same way we did before with the other calculation, where it gives you the number of moles. So you'll start out with the number of moles again, 0.150 moles of aspirin, but I don't want to write out aspirin. We'll just write down this formula, C9H8O4, right? And we begin our dimensional analysis. Right? We begin our dimensional analysis. Well, how did we do it in the last example, right? We can say that for every 1 mole of aspirin, remember we want to go away from aspirin, which is a C9H8O4, and go to oxygen. So we have to try to cancel out aspirin. How do we do that? We start out by putting 1 mole at the bottom, right, of aspirin. And so for every 1 mole of aspirin, right, how many moles of oxygen do we have? Well, the formula says 4. So that's what we put up here, 4 moles of oxygen, right? 4 moles of oxygen. Then we continue our analysis because that's only moles of oxygen. We need to get to atoms of oxygen, right? So we got to cancel out moles of oxygen somehow. Well, 1 mole of oxygen equals how many molecules of oxygen? Remember Avogadro's number, right? So that's 6.02 times 10 to the 23rd molecules of oxygen, right? Molecules of oxygen. And it's simple dimensional analysis now, where you can cancel out moles of aspirin, those cancel, right? And then you cancel out moles of oxygen, those cancel. And now you do the math at the top, multiply at the top, and then divide by the bottom. Well, this is easy because everything is 1 mole down here, so you don't even have to divide by the bottom. So let's just multiply everything at the top. So let's switch over to the calculator real quick. There we go. Clear. So we want to start out with 0.150 times 4 moles of oxygen times Avogadro's number again. So 6.02. And then this is where we do E again. Second E, right, to the 23rd. And then press enter. The calculator gives us 3.612 times 10 to the 23rd. Sorry, there's a little glare on my end here. I can't really see what the calculator says. 23rd, and we do 3 sig figs again, right? Which means it's only going to, the answer will be, we have 3.61 times 10 to the 23rd molecules of oxygen. Pretty simple, right? Pretty simple. The reason why we do all this, though, is so that we can talk about this thing and use this thing called molar mass. Molar mass is the thing that allows you to take a chemical, right? I just happen to have a bottle of pure ethanol right here, right? Can you read that? It's a little bit bright. Yeah, see pure ethanol. Yeah. So molar mass is the thing that allows you to take a bottle or a jar of some chemical that's on the shelf, right, and calculate how much of that you need to make certain concentrations of stuff, right? So let's just go over some formal stuff about it. Molar mass. The molar mass is there's missing a T there. There we go. Is the mass of 1 mole of the element, right? And then that makes it, the atomic mass then is expressed in grams, right? So for example, if we have a carbon atom, 1 mole of a carbon atom equals 12.0 grams of carbon atoms, right? Luckily for us, all these molar masses are on the periodic table, right? Remember, we were talking about the periodic table before and what the molar mass was, and that was an average of all the isotopes, right, of a particular element. Well, it also is 1 mole of all those, the weight of 1 mole of all those averages of all those elements of a particular element, right? So we can use that then as a conversion factor, where 1 mole of carbon, right, is 12.01 grams of carbon. Or you can write it the other way, 12.01 grams of carbon per 1 mole of carbon, right? Either way is correct. Either way is correct. So let me see what the next slide is. I already forgot what the next slide is. There we go. So, oh, I forgot to take off the calculator. Let me show you. We're missing that. There we go. So that's really helpful, like I was saying, because on the periodic table, the very bottom of the element, they all have molar masses. So for example, silver here, its molar mass is 107.9 grams, right? So that's 1 mole of silver atoms is 107.9 grams. So you can say it's 107.9 grams per mole for the silver atom, or the element silver, right? Same thing over here with sulfur. Sulfur has its molar mass down there too, 32.07. What that means then is what? 1 mole of sulfur weighs 32.07 grams. Or you can say, for sulfur, it is 32.07 grams per mole. And that's very helpful, because then you can start figuring out how much things weigh, or to weigh out of things on the shelf, of chemicals on the shelf, to actually make certain concentrations of different solutions, right? Which we'll talk about a lot of that later. So let's do a quick example. So lithium carbonate is a drug that's used to treat bipolar disorder, right? It is an allied health class, so I have to put in some allied health type of, or health type of examples, right? So the question is then, what is the molar mass for lithium carbonate? Well, it's really easy to figure out, because all of the elements on the periodic table have their molar masses already posted there, already right under their symbols, right? And you can use the subscripts, right, to figure out how much there is of each, and then multiply that by its molar mass, right? So let's just do it the way we've been doing it with the dimensional analysis, right? Let's start out with lithium. The formula of lithium carbonate shows that it has 2 lithiums in there, right? So that's 2 moles of lithium. We'll start out our dimensional analysis here. How many mole? So again, we have to try to go from moles of lithium to grams of lithium. So we always say 1 mole of lithium at the bottom to cancel out the grams. And then we look up lithium's molecular weight, right, or atomic weight. And that is 6.94. 94 grams of lithium. Right? Do the quick math there. 2 times 6.94, and we get 13.88 grams of lithium. Right? Let's do that again for carbon in the carbonate ion right there. 1 mole of carbon. For every 1 mole of carbon, we have 12.01 grams of carbon, right? I forgot to cancel up here, just to show you, right? Those cancel out. So here, carbons cancel out, right? You're left with grams of carbon. Well, that's simple. 1 times 12.01 gives you 12.01 grams of carbon. Okay? And then the last element or atom in there is oxygen. There are 3 moles according to the formula of oxygen. We'll start a dimensional analysis there. For every 1 mole of oxygen, it's 16 grams of oxygen, right? Cancel out the moles, we're left with grams, which means all you have to do now is 3 times 16, which is 48.00 grams of oxygen. And now you just need to add up all three of these. To get the total weight, and that is 73.89 grams of lithium carbonate. Right, lithium carbonate. Cool. So that's known, this number here, by the way, is known as the molecular weight, right, of the compound. Right, the molecular weight of the compound. Some people call it the formula weight, but it's most commonly, especially on the back of like chemical bottles, it's mostly, you mostly see it as MW, which stands for molecular weight, right? So I have this bottle of ethanol here for a very particular reason. It's for our next example. So ethanol is abbreviated ETOH, right? Its formula is C2H5OH. So the ET for ethanol comes from the word, or the prefix ethyl, which is that part right there, right? The C2H5 part. And then this part here is called the hydroxyl. It's called the hydroxyl. Put them together and get ethanol. I'm thinking I need a beer right now. Anyway, so you'll learn a lot more about ethyl groups and hydroxyl groups and all that in our organic chemistry section of the lecture later on in the semester. Its structure looks like this. So let's figure out its molecular formula. First thing to do is that we see that we have 2 carbons here, right? Which means that's 2 moles of carbon. So we'll start out by saying 2 moles of carbon. And we'll do our dimensional analysis. We want to cancel out carbon, so we'll put 1 mole of carbon at the bottom here to its molecular weight. What's the molecular weight of carbon? Anybody remember? Yes, it is 12.01 grams of carbon, right? So that's a simple dimensional analysis right there. Moles of carbon cancel out. You're left with 2 times 12.01, and easy stuff there, 24.02 grams of carbon, right? Then the next thing in line in the formula here is the hydrogen. We have 5 hydrogens there and 1 extra hydrogen there, so that means we have 6 total moles of hydrogen. Same process again, we want to cancel hydrogen moles, so we'll put 1 mole of hydrogen at the bottom, right? And what's the molecular weight of hydrogen? I'll just go ahead and tell you, it's 1.008 grams of hydrogen. Again, another simple thing here, we just want to multiply 6 times 1.008 because 1 is already down there. We'll cancel out moles of hydrogen, we're left with grams of hydrogen. And the what we get there now is 6.048 grams of hydrogen. Right? And the very last thing we have is 1 oxygen. And so we'll start out by just saying again, sorry, I lost my train of thought. 1 mole of oxygen, because we have 1 oxygen in the formula. Again, we want to cancel out moles of oxygen, so we'll put 1 mole of oxygen down there at the bottom too. And then we'll put in the molecular weight of oxygen. Anybody remember? It was in our last example. 16, not 12. 16.00 grams of oxygen. Right? Really simple there. Just 1 mole, so we just say 1 mole times 16 is just 16 grams of oxygen. Right? Moles cancel out. We add it all up, right? And we'll go ahead and round it as well because we need to get to the right number of significant figures. That all is 46. Let me write that again. 46.07 grams of ethanol. That's its molecular weight. That's ethanol's molecular weight. So the reason I have the bottle of ethanol here is to show you that we just calculated the molecular weight of ethanol, right, as 46.07 grams. And if you look at the back of the bottle here, I'm going to switch over to the calculator view so you can see this a little bit better. I'm going to move the calculator out of the way and put the bottle in its place. Molecular weight, 46.07 grams per mole. See? So that's why we did that. All right, so let's keep going. Let's keep going. A lot of calculations in this particular lecture. Let's see here. The next slide, sorry. So now we can continue doing our calculations using molar mass. In this particular example, we have a box of table salt that has 737 grams of sodium chloride in it. We want to know how many moles of sodium chloride are there, right? Well, given that amount that's present and the molecular formula, we can actually figure that out. Notice that there's only 1 mole of sodium in the formula, right? Because there's no subscript, so that's understood as 1. And then as far as chlorine, or in this case chloride, there's also 1 mole of that because there's no subscript present. So the first thing we have to do is figure out what the molar mass is of sodium chloride to figure out how many moles there are present in the box. How do we do that? Well, we'll use our molar ratios there given to us by our formula. So we have 1 mole of sodium times its molecular weight, which is 22.9 grams per mole, right? And I don't know why I wrote it that way for you. I should write it dimensional analysis way, which is what we've been doing. So 1 mole of sodium present there in the formula. And then for every 1 mole of sodium, there is, if you look on the periodic table, its molecular weight is, or atomic weight is 22.9 grams, right? Those cancel out, so you're left with just 22.9 grams of sodium. We'll do the same thing with chlorine or chloride here. We have 1 mole of Cl. 1 mole of Cl at the bottom too, because we want to cancel out Cl to get to grams, right? And so we'll put in the atomic weight of Cl, which is 58.4 grams of Cl. Cool. 1, 1. That means that says 1 times 58.4. We'll just put that right here. That's the answer there. 58.44 grams of Cl. Right? So to get the molecular weight of the entire formula, we just add those two together. So let's do that on the calculator together. Okay. Clear. 22.9 plus 58.44. Let me make sure I typed it in right. Yep. I didn't actually. I put a plus sign there. Make sure you're being careful about how you're typing things in. There we go. There's a plus sign right there that actually needs to be a point. There we go. Press enter. And our total is 81.34. grams per mole for sodium chloride. Okay. Now, how do we figure out how many moles there are? Remember the molar ratio we can use, right? We can either do 81.34 grams of NaCl over 1 mole. Oops, 1 mole of NaCl. Right? Or we can do 1 mole of NaCl over 81.34 grams of NaCl. We'll decide that by starting our dimensional analysis. We have grams of NaCl already, right, in the question, 737 grams NaCl. We want to cancel out grams to get to moles, so we'll use this one. 81.34 grams NaCl, NaCl to 1 mole. NaCl, what am I doing? NaCl, there we go. What does that equal? Pretty simple, all we have to do is multiply the 737 times the 1 mole and then divide it by 81.34. Right, so let's go ahead and clear. And then type in 737 divided by 81.34. Oops. See, just tiny little mistypes. Make sure you're catching yourself when you're doing your test and stuff, right? Enter, and that gives us about 9 moles. We'll go to 3 significant figures for right there, right? 3 sig figs. So 9.06 moles of NaCl. And that's how you would calculate that out. Right? That's how you calculate that out. So the next thing on the slide is a little chart that helps you figure it all out, kind of like a shortcut chart to show you how the relationships and how to go back and forth between them. Let me erase the work there so you can actually see it. Again, if you needed to write all that down, just pause the video. But yeah, that's just a little summary chart of all the molar calculations that we just did. All right, summary chart. So that takes us then to chemical reactions, but let me actually minimize the calculator first. There we go. There we go. Chemical reactions. So the equations for chemical reactions are pretty self-explanatory, right? We start out with reactants. Sometimes there's one reactant, sometimes there's 2 reactants, right? But the reactants are always going to be on the left side of the arrow, and then on the right side of the arrow are the products. Sometimes there's 1 product, sometimes there's 2 products. So this part right here is called the reaction arrow. Whenever there's a little delta right there, that means heat, right? And so heat is being applied to the reaction. So in the example that they have here, we have carbon, right? Solid carbon combining with oxygen gas to make CO2 gas, right? To make CO2 gas. That's what we're seeing there, right? So just remember, as we go through and look at all these chemical reactions, equations for chemical reactions, right? The plus sign separates 2 or more different products or reactants in the equation, right? The arrow is the reaction arrow to form the product. So the reactants are always going to be on the left side of the arrow. The products are going to be on the right side of the arrow. So also, we put the state of the component in the reaction in the equation for the reaction. For example, here, the carbon here has an S next to it. That means a solid, which means that's solid carbon. And then the oxygen has a G next to it, which means it's gas, right? We also have liquid too. And then we also have aqueous, which is AQ. So AQ just means that it's something in solution. An example of that would be something like salt water, right? If you had some salt water and you wanted to write it like it was in a chemical equation, it would be NaCl AQ, right? So that's an in solution. That's something that's in solution, right? And then, as I already said before, when there's a triangle there, that's heat. So now that you're familiar with what a chemical reaction equation looks like, let's talk about balancing chemical equations, right? So things to remember, and remember when I always have these kind of definition things actually typed out on the slide, it means it's important, right? So in balancing chemical equations, know that no atoms are ever lost or gained, right? And the number of atoms on the right side or the left side, the reactant side, is always equal to the number of atoms on the product side or the right side, right? So there's no creation or there's no destruction, right, of matter here or any atoms. It has to be equal on both sides. So that's what we're going to do now. Let's balance some chemical equations. So let's take a look at our first example here. It's pretty simple, right? We have some solid aluminum and we have some solid sulfur, right? Solid aluminum, solid sulfur. When they combine with each other, they make aluminum sulfide right here, right? They make aluminum sulfide. But if you look at the subscripts in the formula, there's 2 moles of aluminum here. And then on sulfur, there's 3 moles of sulfur. 3 moles of sulfur. Well, that's not good, because on this side of the equation, there's only 1 mole of aluminum, and there's only 1 mole of sulfur, right? So how do we make it so that this equation is balanced? Quite simple, right? Because all you need to do then is make it so that there are 3 moles of aluminum plus 3 moles, I'm sorry, 2 moles of aluminum. Let me write that again. 2 moles of aluminum plus 3 moles of sulfur, right? And don't forget your states, those are important. And that makes aluminum sulfide, which is also solid. And now you're balanced. 2 aluminums on both sides and 3 sulfurs on both sides, right? 3 sulfurs on both sides. So basically, when you add a number to the front of an atom or a reactant, that's like a multiplier. You're multiplying that number of atoms. So you had 1 mole of aluminum here, but you multiply that by 2 moles of aluminum so that you can have the same number of moles of aluminum on the left side as you do on the right side, on the product side, right? We'll use that a lot, actually, to balance chemical equations. So let's do another example. I'm going to have to clear this so we can actually read the whole thing. There we go. Let's balance a chemical equation when solid iron oxide reacts with hydrogen gas to produce solid iron in water, right? So just with the information that's in this question, you can actually write out a chemical equation. It won't be balanced yet because you got to balance it yourself, but you can at least get the base equation written, right? So it gives you the reactants right here, which is Fe3O4, iron oxide, right? And you're adding it to hydrogen gas. And remember, hydrogen gas is a diatomic. It's always H2, right? And then also, don't forget about your states. I always forget about the states. So that's solid, and it's hydrogen gas. So it's G for gas. And it tells that your product here is solid iron, which is just Fe, right? And water, H2O, right? And water is a liquid, and then iron is a solid, right? So what are we going to do to balance this equation, right? What are we going to do to balance this equation? Well, let's first look at the all the different number of moles of all the different components of all the different reactants and products, right? Over here, we have a total of 4 moles of oxygen, and over here we only have 1 mole of oxygen, right? Over here on the reactants we have 3 moles of iron, and we have 1 mole of iron there, right? Notice we're not going to mess with any subscripts, right? We're just going to add in multipliers. And then over here we have 2 moles of hydrogen, but over here we also have 2 moles of hydrogen, so that's good, right? So let's see here. How do we get it so that we can still have the same number of moles of hydrogen, right? But then have also 4 moles of oxygen. Well, it's pretty simple because since there's only 1 mole of oxygen here, you can actually add a multiplier of 4 in front of that, and now you have 4 moles of water, but there's only 4 moles of oxygen too. But now you have 4 in front of the hydrogen gas, which is H2 as well, right? So 4 times 2 hydrogen gases makes that 8 moles of hydrogen gas. How do we get 8 moles over here now on the reactant side? Well, that's pretty easy, right? Because we already have 2 moles of hydrogen there. We put a 4 in front of that, we also get 8 moles of hydrogen on the reactant side, right? Cool. Now we're left with balancing the iron. There are 3 irons over here, right? 3 moles of iron over here. We just need 3 moles of iron over here, and lucky for us, iron is by itself. It's solid, solid by itself. So all we have to do is put the 3 in front of that, in front of the iron. And now we have 3 moles of iron on both sides. So quick review, right? Quick review. We started out with the oxygens. There's only 1 oxygen over here, right? But there are 4 over here. 1 oxygen on the product side, but 4 oxygens over here. So we have to somehow match the amount of oxygens there are on the reactants to the product side. The easiest way to do that is just to put a 4 in front of the water, right? And that gives us 4 oxygens. But then that also gave us 8 hydrogens, right? Because 4 times 2 is 8 hydrogens. So how do we get 8 hydrogens on the reactant side now, right? Well, simple. You put a 4 in front of the hydrogens, now you have 8 hydrogens, right? On both sides. And then we were lucky enough where iron on the product side there was only 1 of them, and then we had 3 irons on the reactant side. So just to match up and balance the 3 irons from the reactant side with the 1 iron that's on the product side, all we had to do was multiply that by 3, right? So our finished chemical equation then balanced is Fe3O4 solid plus 4H2 gas makes 3 Fe solid and 4 waters liquid. Pretty easy. All right, let's do another example. And I have to clear it again because I wrote on it. There we go. Now we're doing it with a polyatomic right here. Remember the polyatomics? This right here is a phosphate ion. Phosphate ion. Right? That's a polyatomic right there. And remember, polyatomics are groups of multiple atoms put together, usually nonmetals, that have their own overall charge. So in this case, you need to treat phosphate like this, right? Where it's together. So that means there's only 1 mole of phosphate on this side. Let me just write that again because I got really unclear right there. Let me see here. There we go. So that's phosphate. That's a phosphate ion right there, right? And to start out this, a lot of students make a mistake here, right? You need to treat the phosphate as a group, right? And altogether, this phosphate here only has 1 mole because there's no subscript. Now this is why you have to remember the polyatomics, because the polyatomics are balanced in such a way where the entire polyatomic is being balanced, not the individual atoms separately, right? A lot of people try to balance out the phosphorus separately and the oxygen separately. That's when you go wrong. So 1 mole of phosphate right there. I'm going to write this over here just because we can't see it because I wrote over it. That's 3 moles of sodium, right? So that's sodium phosphate, which is dissolved in a solution of water, aqueous, right? plus magnesium chloride, also aqueous, and our products are then magnesium phosphate and sodium chloride, right? So let's go ahead and balance this equation out. Let's balance this equation out, right? Just to make things easier on us, right? Let's write out the moles of everything. We already got the sodium phosphate over here, but magnesium we have 1 mole of Mg, and then chloride we have 2 moles of chloride, right? And then over here on the product side we have 3 moles of Mg. We have 2 moles of phosphate, right? Different from over here where we only had 1 mole on the reactant side. And then we have 1 mole each of sodium and chlorine. Right? We have 1 mole each of those, right? All right, so how do we start out by doing this, right? Well, the first thing to notice is that one of the largest things we have to balance out is the fact that there's 3 sodium moles on one side, on the reactant side, and only 1 sodium over here, right? Only 1 sodium over here, okay? So only 1 sodium over here. So the first inclination actually is to say, okay, since I have 3 moles of sodium on the reactant side, I'm going to put 3 moles of, put a multiplier of 3 in front of sodium over here to make 3 sodiums over on the product side. So the problem with that though is that you have you have chlorine right here too, or chloride right there too. And so that means that you're going to have 3 moles of chloride too on the product side. You go back over to the reactant side, you have 2 moles over here of chloride, right? Uh-oh. How do we do that? We have 3 moles of chloride on the product side, and we have 2 moles of chloride on the reactant side. Well, so this is one of those cases where to balance it, you're going to have to go with the lowest common multiple, right? Because what happens then is that what you can do is multiply the chlorine over here, right, which there's 2 moles of, by 3, by putting a 3 in front of the Mg, right, the Mg chloride, the magnesium chloride. That gives us 3 moles of magnesium, and then 3 times 2 moles of chlorine gives us a total of 6 moles of chlorine, right? Awesome. And then over here we can put a 6 in front of the sodium chloride, and then now that gives us 6 moles of chlorine to match both sides, right? There's 6 chlorine moles on both sides of the equation now. Oh no, but that means we have 6 sodiums too. How do we balance that on the other side of the equation with the reactants? Well, remember we have 3 already. To get to 6, all we need to do is put a 2 in front. 2 times 3 equals 6 total sodiums, right? 6 total sodium moles. So now we have 6 sodiums total on the reactant side, and we have 6 sodiums total on the product side. Great. Oh no, but we forgot. We have the phosphate ion in here, and there's only 1 of them. But actually, since there's 2 in front of the entire formula, in front of sodium phosphate, right? It's 2 times 1 phosphate, which makes that 2 phosphates. 2 moles of phosphate. Well, that's happy. How many phosphates do we have on the product side? We already had 2 on the product side. Right? So that worked out pretty well for us. Right? And since you put a 3 in front of the magnesium there, we had 3 moles of magnesium there. And look at that. The subscript shows that there's also 3 moles of magnesium on the product side. That's great. So everything worked out, right? It's all balanced now. So you'll see you'll notice that when you work out these balancing equation problems, that fixing a couple things will actually fix the entire equation, right? And if it doesn't work out that way, then you've done something wrong. You've used the wrong multiple in the front or something like that, right? So the final equation is going to be then, the final balanced equation is going to be 2 sodium phosphates plus 3 magnesium chlorides produce 1 magnesium phosphate plus 6 sodium chlorides. And don't forget your states of matter. That's a solid right there. That's also a solid right there. That's also a solid. And that's a solid. Right? That's your completed balanced chemical equation for the reaction of sodium phosphate and magnesium chloride. So now let's talk about the different types of chemical reactions, right? And we'll have a little run of like 6 or 7 slides with no calculations. Thank God, right? Anyway, these are the type of chemical reactions we'll be talking about, right, in this particular section. They're combination reactions, decomposition reactions, single replacement reactions, double replacement reactions, and combustion reactions. Let's go through each one of these one by one. The first one is a combination reaction, right? And this slide is very helpful because it has everything on it that you need to know about this type of reaction, right? It's normally 2 or more elements form one product. That's a combination reaction, right? That's a combination. Simple compounds combine to form one compound, right? So that's A plus B makes AB. What does that mean then? That means then that in a combination reaction, the components will add together to become the new product, right? The new product. And we have an example here. We've got magnesium solid here, and it's reacting with oxygen gas with some heat applied. Don't forget about the triangle, which means heat, right? You can't see what I wrote there. Sorry, my head's in the way. Heat. There we go. And then it gives us magnesium oxide. Now that's the quintessential combination reaction. Pretty simple. The next type of reaction is called a decomposition reaction. It's basically the opposite of a combination reaction, where you have a reactant, AB, and it breaks down into A plus B, right? One substance splits into 2 or more simpler substances, right? So that's what's happening here in this particular reaction, where we have mercury oxide, right? You get some heat applied to it right there. Big triangle for heat right there. And your constituent atoms break apart, and you get mercury, liquid mercury, right? 2 moles of that, and oxygen gas, right? Oxygen gas. Exactly the same thing as a combination reaction in reverse, right? Combination reaction is 2 things put together, make one product. Decomposition reaction is one product or one reactant breaks apart to become 2 products, right? 2 products. Next type of reaction is called the single replacement reaction. Single replacement reaction, right? So usually what happens here is that one element takes the place of another element in a reacting compound, right? So here we have A is one element, and then we have a compound BC, and then it replaces A replaces B in BC to make AC plus B, right? Single replacement. So only one of the constituent atoms or elements is replaced. That's why it's called single replacement, right? Single replacement. So in this particular example that we have here, we have zinc solid reacting with hydrochloric acid, right? And hydrogen gas is released, being replaced by zinc to make a zinc chloride, right? To make zinc chloride. That's a single replacement reaction. Can you guess what the next one is? It's a double replacement reaction, right? Where you have two reactant compounds, right? And they replace each other. Both get replaced, right? Both get replaced. Where AB reacts with CD to make AD and CB, right? Double replacement, because both constituents get replaced. And in this example, we have sodium sulfate reacts with barium chloride, right? And that makes barium sulfate and sodium chloride, right? So in sodium sulfate, the sulfate got replaced by the chloride. And then in barium chloride, the chloride got replaced by the sulfate. Double replacement, right? Pretty self-explanatory. And then last of the reactions that are pretty simple is called the combustion reaction. This is actually a real photo of my propane grill right there, by the way. And I also have a really hard time getting it started, so feel lucky that I was able to get it started to take a picture of it to use as an example for you there, right? Why do I have a picture of my propane grill? Because it's the quintessential example of a combustion reaction, right? Where we start out with something like this, a hydrocarbon, C3H8, which is actually propane, right? There are a bunch of hydrocarbons. So hydrocarbons are just, they're exactly what they sound. They're molecules that are all made of carbon and hydrogen, right? So in propane, there are three hydrogens and three carbons and 8 hydrogens, right? And if I combine that with oxygen gas, which everybody knows that the fuel for anything burning is oxygen, right? We'll get heat, of course, and then out of the combustion reaction, we'll get carbon dioxide and water. And then a whole bunch of energy, which I use to grill my steak, right? So yeah, that's a combustion reaction. The example ahead before it is just methane. Methane plus oxygen also makes carbon dioxide and water and a whole bunch of energy, right? Methane gas, right? So that, I guess that would be gas stoves and stuff. I guess I could have taken a picture of my gas stove. That would have been easier, but oh well. So just a quick review. In a combustion reaction, you'll always get hydrocarbons, right, that burn with oxygen to form carbon dioxide and water. So whenever I'm asking you to identify this type of reaction, if it's got carbon dioxide and water in it, you know for a fact that it is a combustion reaction, right? Combustion reaction. All right. We're just flying through these slides now. This is just for your benefit. The next slide is just a summary of the different types of reactions that we just went through: combination, decomposition, single replacement, double replacement, and combustion. Very helpful for the questions that are going to be about identify this type of reaction. So, yes. So the next type of reaction we keep a little bit separate because it's a little bit more complicated. And these are called oxidation reduction reactions. There we go. Forgot to hit the slide button. So what is an oxidation reduction reaction? It's a reaction in which electrons are transferred from one reactant to another reactant, right? And so the thing that you need to remember here is that these types of reactions are very prevalent in our food. We eat food, and it's an oxidation reaction that gives us the energy from our food, right? Some of you may have heard of the phrase oxidative phosphorylation. We'll talk about that later, though, in the semester. It's a good time. I'm a biochemist, so I really like that stuff, right? It provides electrical energy and in the form of batteries, because batteries are also a oxidation reduction reaction, right? So let's take a look at a few examples of oxidation reactions, right? The Statue of Liberty, right, when was given to us by France, I believe. France gave us the Statue of Liberty. Yes, has a green patina on it, right? It used to not be green though; it used to be like copper colored. So what happened was that over time, the copper metal was getting oxidized and turned green. So here we go with the reaction. We had copper metal from the Statue of Liberty right there, right? And it was losing electrons. And when you lose electrons, it's called oxidation, right? And then those electrons were going to oxygen. And remember what I said a while back? Oxygen is electronegative, so it loves electrons, right? So that's why it's doing it. And that's called reduction. So copper, remember, copper is losing electrons. Electrons are on the reactant side right there. Sorry, the product side. They're on the product side right there. That is an oxidation reaction. Oxygen, though, has electrons on the reactant side, which means it gained electrons. So that's a reduction reaction, right? We can add all those together now and get copper plus oxygen makes copper oxide. And that's why the Statue of Liberty is green now, right? Copper is green. It's when it gets oxidized, it's green. So I guess the mnemonic that everybody uses to remember which is which here is oil rig. All right. So oxidation is loss. That's oil. Oxidation is loss of electrons. And then the rig part is reduction is gain in electrons, right? The electrons go from one reactant to the other reactant, right? And then you have an oxidized product and a reduced product, right? In the case of copper, it became copper oxide, right? So let's do a couple more examples here. All right. So remember what I said before? If the electrons are on the product side, what is this? What kind of reaction is it? It's an oxidation reaction, right? It's an oxidation reaction. If the electrons are on the reactant side or the left side, what kind of reaction is it? It's a reduction. So iron's getting reduced here to iron 2. Right. If you remember, we talked about this before with hemoglobin. Right? When oxygen attaches to iron, right? Before it gets to oxygen, the iron is actually in iron 2. But then when oxygen binds to the iron 2, it becomes iron 3. Because oxygen took iron's electrons. But in this particular example, it's a reduction, right? Because iron actually gained electrons here. And the chlorine gas, gaining 2 electrons there to become chloride, that's also a reduction, right? That's also a reduction. Let's do a couple more examples here. Say I have something like silver ions plus 2 chloride ions, and I end up with solid silver plus chlorine gas. This can happen with exposure to UV radiation, right? Tell me which is the reductant, and which got reduced and which got oxidized. Well, it's pretty simple, right? Because the silver here used to be a +1 charge, and there's 2 of them. So total, it was +2 charge. It had to gain 2 electrons right here, right? It had to gain 2 electrons from chlorine. I don't know what I just wrote there. It had to gain 2 electrons from chlorine. There we go, there's an E. 2 electrons from chlorine, right? Which is nice because chlorine had to give electrons to give up. There's 2 chlorines there because of the multiplier, and there's a minus charge right there, right? So silver had to gain 2 electrons from chlorine to become silver metal, right? And then chlorine lost 2 electrons, becoming chlorine gas, which means that silver got reduced, chlorine got oxidized, right? We can break up this into 2 half reactions now, just to make it more clear. We had 2 chloride ions, and it broke down, getting oxidized into chlorine gas plus 2 electrons, right? So that's why it's an oxidation reaction. Then we had 2 silver ions plus charge, gaining 2 electrons from those chlorines, making solid silver. There's still 2 of them. Oh, I'm sorry, I didn't even realize that you couldn't see it. We'll just cross it out and go down here. 2 solid silvers. Right? So of course that one's the reduction reaction. Right? Remember, electrons on the reactant side, that's a reduction. Electrons on the product side, that is an oxidation. Okay? Cool, cool. That takes us to talking about the conservation of mass. I was just trying to see what time it is. That takes us to the conservation of mass, right? Conservation of mass. Which we danced around a lot already when we were doing all of our calculations and stuff with the moles. But just remember, right, that you need to have 2 moles of iron and 3 moles of sulfur to get to 1 mole of iron sulfide, right? Because that's the formula with the subscripts there. 2 irons, 3 sulfurs. 2 moles of iron, 3 moles of sulfur. So there's also always a conservation of mass, right? You never lose any mass. So a mole to mole ratio, a mole to mole factor is the ratio of the moles of any 2 substances in an equation, which we talked about this a lot already about mole ratios, right? So let's take a look at some mole ratios real quick. Oops, I didn't mean to do that. So let's look at some mole ratios real quick, right? Of this particular compound. So the ratio of, for example, iron and sulfur, right? Of iron and sulfur, we have 2 moles of iron for every 3 moles of sulfur, right? Does that make sense? In that compound, in iron sulfide, which we can also write this way too, which we've done this before in previous examples. 3 moles of sulfur for every 2 moles of iron, right? Cool. How about the ratio between iron and iron sulfide? Right? Well, we see here that there are 2 moles of iron, right, for every 1 mole of iron sulfide, which is going to be written like this. 2 moles of iron for 1 mole of iron sulfide. Or we can write it the other way. 1 mole of iron sulfide for every 2 moles of iron. Right? And last but not least, What about the molar ratio, or yeah, the molar ratio of sulfur and iron sulfide? Well, there are 3 moles of sulfur for every 1 mole of iron sulfide. So the same thing goes again. We can say 3 moles of sulfur for every 1 mole of iron sulfide. Or we can say for every 1 mole of iron sulfide, there is 1 mole of sulfur. And this will be very useful to us later. Very useful. So let's take this example a little further now. Let's take this example a little further now. How many moles of iron oxide can form from 6.0 moles of oxygen, right? 6.0 moles of oxygen. So, how many moles of oxygen are there for every 1 mole, or for every 2 moles of iron oxide? There are 3 moles of oxygen for every 2 moles of iron oxide, right? So we can write that, like we were doing before, as 3 moles of O2 over 2 moles of Fe2O3, or you can write it as for every 2 moles of Fe2O3, you get 3 moles of oxygen. Whoops, throw 3 mole of oxygen. Of oxygen. Of oxygen. There we go. Of oxygen. Okay? That's great. So let's do some calculations now, right? I'll put the calculator on screen. There we go. Start out by using the information they gave us. 6 moles of oxygen. 6.0 moles of O2. Right? And we want to go to moles of iron oxide because it's asking you how many moles of iron oxide there's going to be, right? So we'll do our dimensional analysis, right? And we want to cancel out moles of oxygen so we can get to moles of iron oxide. And I'm not sure why that there's a 1 there, so that's a, it's 3. There we go. 3 moles of oxygen. We're using this one, by the way, if you didn't know, right? 2 moles of iron oxide. Easy stuff, right? 6 times 2 at the top is what? 12, right? And then 12 divided by 3 is 4. So that gives us 4 moles of... See, this is what happens when you forget to cross things out. Moles of oxygen go away, right? You're only left with moles of iron oxide left. So it should be 4 moles of iron oxide. 4 moles of iron oxide, right? We can take this a little further too. Like, how many grams of iron oxide is that? Right? How many grams of iron oxide is that? Well, this is simple, right? Because we already did gram per mole calculations before in the lecture. So let's start out with this. 4.0 moles of iron oxide. So I want to cancel out moles of iron oxide, so I'll put 1 mole of iron oxide at the bottom. right? What do I put up there to figure out the number of grams of iron oxide I made from 6 moles of oxygen? Well, you use the molecular weight of iron oxide. How do you figure out what that is? Well, you look on the periodic table and you add up all the weights of the oxygens, and you add up all the weights of all the irons, and then you get and that's its molecular weight for iron oxide. And I already did that calculation for you, which is 159.687 grams of iron oxide. Right? So I'll cancel that, cancel out moles of that, right? Multiply that by 4, the molecular weight by 4, and that gives me 630, try that again, 638.71 grams of iron oxide. So we can continue on with our mass calculations, right, with this example. Okay? How many grams of oxygen are needed to produce 45.8 grams of iron oxide using this reaction, right? Using that reaction. It's the same one we had last time. Right? So let's start out with what they give us. We've got 45.8 grams of iron oxide. Everything's done with dimensional analysis, right? Everything's done there. And we want to get rid of grams of that, so what do we use there? We'll use our molecular weight of iron oxide that we had from the previous slide. So that's 159.687 grams of iron oxide. Right, of iron oxide. For every 1 mole of iron oxide. Okay, cool. Where are we heading to? Well, we're heading to grams of oxygen, right? So we've got 1 mole of iron oxide already up there. We need to cancel out moles of iron oxide, right? So we'll put, and if we remember from the equation, there are 2 moles of iron oxide for every 3 moles of oxygen, right? So we'll put 2 moles of iron oxide down here. And then we'll put 3 moles of oxygen. Oops, there we go. Of oxygen, or O2, there. Alright? We're almost done. We're almost there. Now we have grams of oxygen. Now we have moles of oxygen, and we want to get to grams of oxygen. So we need to use the molecular weight of oxygen now, right? So for 1 mole of oxygen, right? So this is O2, oxygen. So there's 2 oxygens there. So you'll have to multiply the molecular weight of 1 atom of oxygen by 2, because there's 2 atoms of oxygen there. So that means that's 16 from the periodic table, right? Times 2, which means that's 32 grams of oxygen. Or O2, right? 32 grams of O2. So let's do this on the calculator real quick. Maybe there was a reason why I had this calculator view up. I think I forgot to do that in the last slide, but that's okay. We're doing it this time. So let's multiply across 45.8, right? Times 1 times 3 times 32, right? And then divide that by 159 point, we'll just do, 687 0.687. Forgot to put the parentheses around here because we need to do the top first. So let's go and add in parentheses. Second, insert a parentheses. Yes. The top first. Okay, so 159.687 times 2, and then times 1. And then we'll close the parentheses. Before we hit enter there, let's just go cancel stuff out. We have grams of iron oxide getting canceled out with grams of iron oxide. Then we have moles of iron oxide being canceled out with moles of iron oxide. Then we have moles of oxygen being canceled out with moles of oxygen. That leaves us with just grams of oxygen right here as our last unit. Right? Grams of oxygen are our last unit. Let's press enter now. And the calculator gives us a really long number. $13.76693 ... right? A whole bunch of numbers there. Our lowest number of sig figs is right here, 3 sig figs. Which means we'll take this down to 3 sig figs here. Our answer then will be 13.8 grams of oxygen is required to produce 45.8 grams of iron oxide. Right? You see how all these molar calculations all kind of fit together after you learn each part of it? It's kind of fun. Kind of fun. So let me see here. Let me look at my notes real quick here and see how much we have left. We only have a couple slides left, and we'll be done here with this one. So our next couple of slides are going to deal with the energy that's involved in chemical reactions, right? So at the very least, for a chemical reaction to occur, you have to have 3 things. The first thing is collision, right? These molecules, say they're salt molecules, sodium chloride molecules, and water, they're moving around a lot, right? And they actually have to collide with another molecule different from themselves, right? Being in physical contact with that other molecule for a reaction to proceed. So that's the first criteria for a chemical reaction to occur. The second one is orientation. That sodium chloride molecule has to be orientated in such a way that when it collides with that other molecule, like the right atoms are touching for it to be, for the reaction to proceed as well, right? It has to be, if it's not in the perfect orientation for the energies to be right, it won't happen, right? And last but not least, there has to be enough energy that is released or in the actual collision itself, right, to get to the activation energy of that reaction, right, or to provide enough energy to actually activate the reaction itself, right? So we call that the energy of activation. And we'll talk about ways to make these things happen more readily in a minute. Those are called catalysts, right? But let's talk about the basic reaction first, right? The most basic of reactions first. So these are 2 energy plots of the 2 types of reactions that can occur, right? There's the exothermic reaction right here, and then there's the endothermic reaction right there, right? And if you look at these plots, right, you see this line. Well, let's look at the axes first. You have the progress of the reaction on the x-axis, and you have the energy of the reaction on the y-axis, right? So the reactants are always on this side of the curve, and the products are always on this side of the curve. And so what's happening here is that reactants will react with each other to provide products, right, so that they can be more lower in energy. They can become more stable, because the less energy you have, the more stable you are, right? But it costs something for them to do that, right? These reactants have to have enough energy. They have to pay enough energy, right, for them to be able to reach this level called the activation energy right here, for them to become a new compound and then relax back down, right? Or not relax, but stabilize back down as their new product, right? So there's always a cost involved. There's always a cost involved. So yes, this is the activation energy, this gap right here. And that gap is the gap that is between the energy of the reactant itself and the energy required to activate the reaction so that they become more stable products and become lowest energy as possible, right? That's like the goal of most things, especially in chemistry, to become more stable, okay? To become more stable. In an endothermic reaction, right? In an endothermic reaction, it's kind of the opposite, where the same thing is happening here, right? Where you have reactants, and the activation energy is very large, for the reactants to become a new product. But they don't become more stable products because they actually absorb heat. They absorb more energy, right? And so that's an endothermic reaction. So that's the difference. In an exothermic reaction, you're releasing energy, right? And an endothermic reaction, you're absorbing energy, right? And you might be asking yourself, why would two reactants want to do that? Begin at lower energy, but then after they react, become higher energy, when the goal of all reactants or most things in nature is to become more stable, right? Well, it's because there could be multiple steps after this reaction where those products can actually react with other reactants, right, and become even less energetic, right? That's why. But this is just the first step. So, in this particular example here, we have carbon, we have solid carbon, right, and hydrogen gas combine with each other to make methane gas. And when that happens, 18 kilocalories of energy is released. So that is an exothermic reaction. Remember that if there is energy on the product side, that's going to be an exothermic reaction. Okay? Over here we have nitrogen gas and we have oxygen gas plus energy on the reactant side, so there needs to be energy put into it, right? Like right up here in this graph. And we get dinitrogen oxide gas, right? So when the energy is on the reactant side, that is an endothermic reaction. Remember that, right? Remember that, right? All this to say is that we can actually measure what we call rates of reactions. Right? We can measure what we call rates of reactions. That says rates. I don't know why it turned out so bad. Rates of reactions. That still turned out pretty bad. And basically what a rate of reaction is, it's the speed that a reactant is used up and products are formed, right? And things that can actually speed up rates of reaction are temperature, an increase in temperature, which makes sense because you're adding more energy to the reaction, right? And you have to make over this hump right here, right, called the activation energy. So the more heat or the more energy put into reaction, the easier it is for a reactant to get to the two reactants to get to the activation energy or the energy hump to make its products, right? So temperature is one of them. But another thing that also can increase the rate of reaction is increasing the concentration of the reactants, right? Increasing the concentration of reactants, right? What that basically means is putting more carbon in there, right? Or putting more hydrogen in there, or putting more nitrogen in there and more oxygen in there. In an endothermic reaction, you can speed up the energy, speed up the reaction, the rate of reaction by adding more nitrogen, by adding more oxygen, and by adding more energy, more heat. See? Does that make sense? That's all I really want you to know about these particular things, these particular concepts. And then the very last slide we're going to talk about is about catalysts. So I'm a biochemist, right? That's what I was trained to do. And in biochemistry, we talk about enzymes. Enzymes are catalysts. They are there to help the body do chemical reactions that provided energy or provided structure, right? So what is a catalyst? Well, a catalyst increases the rate of reaction, right? Kind of like heat does. Or kind of like, adding more products to, or more reactants, right? How does it do that, though? So unlike the previous slide where we were adding heat or adding more products, there the activation energy actually stays the same, right? When you add heat or more reactants, that will speed up the reaction, but the actual activation energy required to proceed with the reaction to get over that hump stays the same. The difference here is that in catalysts, it actually lowers the activation energy, right? Catalysts will actually make the activation energy lower so that the reactants don't need as much energy to get over that hump to make its products. And the biggest thing is that a catalyst is not used up during the reaction, right? Not used up during the reaction. That's the biggest thing. That's why our bodies use enzymes, right? Because they lowered the activation energy for less favorable reactions that we need to make energy or structure, right? And they're never used up. So, just as a little aside, not aside, but a little summary, just to help you remember things, as far as increasing rates of reaction, if you increase the temperature, what does that do? That makes more collisions, right? And more energy to activate. But remember, though, that the activation energy stays the same. Same thing with increasing the reactants, the concentration, more collisions, but the activation energy stays the same. But if you add a catalyst, the catalyst will lower the activation energy so that the reactant can proceed with its reaction with less energy involved, right? That it has to put in. How does it do that, you might ask? Well, in biochemistry, enzymes will actually make the environment around the reactants more favorable, right? Like they'll put different atoms in different parts of the molecule in certain places so that surrounding it by a microenvironment, making it more favorable, right? Lowering the activation energy so that it wants to do this. Because you can't use heat, right? If you heat up the body while it's alive and you're trying to make a reaction happen, that's bad, right? Anyway, so that ends this particular lecture.